Hi everyone, this is Ramesh. I'll be presenting the LEGOStore paper today, which is a strongly consistent geo-distributed key value store that combines replication and erasure coding. So just before we get started, I just wanted to call out that there is a pretty good YouTube video for a presentation on this paper that is present on YouTube by one of the authors. I watched it a few times to parse through the paper, and I borrowed some content from their slide deck here because it was summarized so nicely there. So in case you haven't, please you can go ahead and check out this presentation from one of the authors. With that, let's get started. I'll start the slideshow. Yeah, so I'll go over the sections as they are in the paper. So I'll go through the introduction first, then the background, then the design of the system, and then the results and key insights. So let's start with the introduction. So what is LEGOStore? So it's a key value store. That means it provides a get input interface for placing objects in cloud. It is cloud-based, so it provisions resources from a cloud provider and pays for them. It is geographically distributed for a couple of reasons. One is fault tolerance. It can survive machine failures, rack failures, even data center failures. And it has a global user base, as many of the applications are required to be geographically distributed, uh, just because users could be located across the globe. It is strongly consistent, and it provides non-blocking concurrent operations to the same key. So some of the concerns with the geographically distributed, strongly consistent KV stores are higher latency, especially if the key is to be replicated across data centers that are geographically distributed. It's difficult to hide the latency, and along with it come cost overhead for, especially for inter-DC networking costs. And there are challenges to meet performance goals for such a system on an ongoing basis, especially due to dynamism in the system, which is a shift in predicted traffic. A new clients could appear in new locations that are far from where the data is stored. There could be hardware failures, as I mentioned. Machines could fail, racks could fail, entire data centers could fail, and there could be increase in network delays, which can lead to degradation. So with Lego stores, the design goals of the system are predictable tail latencies, SLAs, uh, low cost of operations, and robust in the face of dynamism. So all these factors that I mentioned. So if these change, then the system should be able to adapt. So with that, let's move into background. So typically, when we discuss systems in cloud, we assume constant pricing and network latencies across various regions in the cloud. But that is not exactly true. So there exists an arbitrage where, for example, over here, this is a table comparing some of the data centers in GCP. So it specifically compares the latency between two data centers and the network price for dollars per GB. So for example, between London and Frankfurt, it costs 8 cents to transfer a GB, and the latency is 15 milliseconds. And whereas between Tokyo and Sydney, it could be double that price and 10 times the latency. So that could affect cost and performance significantly. Similarly, for storage and VM costs, there also exists an arbitrage, not as great as network latencies and pricing. So for example, here, Oregon is the cheapest with 4 cents for per GB per month, and I think little more than 2 cents per hour for virtual machines, whereas Sao Paulo is roughly 50% more than that. So this information is something that LEGOStore makes use of to constantly optimize the costs on an ongoing basis. Another thing it makes use of is the erasure coding. So typically, these data stores make use of replication. So this paper explores erasure coding as an alternative to data replication and in the system design. So just a brief primer. So with the erasure coding, our data chunk is split into parts. Over here, data chunk is split into 4 parts, and then we calculate some parity chunks to it and store it across uh, some servers. So here, these two variables are configurable. So k is the number of chunks, which is 4 over here, and n is the number of servers across which it's stored. So 4 original chunks and 2 parity chunks, so stored across 6 servers. And the data is recoverable from any of these 4 chunks, and each chunk is b by k bits, where b is the original size of the chunk. The erasure coding is widely used across archival systems, especially in the same data center. But this paper explores it in a strongly consistent system, which is geographically distributed across multiple data centers. So let's go into the design. So there are 3 key design ideas with the system. So one is use of quorum-based, strongly consistent non-blocking protocols for get and put operations. Another design idea is an optimization framework that that is constantly optimizing the placement of keys to give the best performance and cost out of the system. And reconfiguration is another aspect. So this optimization is running frequently. So the system knows when to reconfigure the configuration of the keys so that the system is optimized and is meeting its performance and cost goals. So some details on this. So first is the linearizable non-blocking protocols for get-put operations. So there are 2 protocols that are used. First one is a replication protocol called the ABD algorithm, which is a classical algorithm, which uses a quorum, a majority quorum, and logical timestamps to ensure consistent ordering. It has a two round put and a 2-round get. And another algorithm that is compatible with erasure coding is the coded atomic storage CAS, which is a known algorithm. It uses a NK erasure code. We discussed NK previously when we discussed erasure coding, and it requires a quorum of K nodes which have the K chunks to reconstruct the value. Or write it to K nodes, and it has a 3-phase put. So one difference between ABD and CAS is there is one extra round in the put, and it has a 2-phase get. Just comparing these algorithms at a high level. So with ABD and CAS, the put usually as K increases, the CAS cost decreases. However, there is a additional round for put, and the quorum sizes are larger in CAS because it requires K nodes. As the size of K increases, the requirement for quorum size increases as well. So there's bound to be a latency penalty. And one small bit of difference is in the get round. So when it's writing back data in the get round, ABD writes the full data back, whereas CAS is just writing the metadata. So it's smaller overhead on the network. So coming to the optimization, so there is this concept of epoch, which is a period of time for which the workload features are stable, and as a result, latencies are stable. So the solver solves for a configuration an optimized configuration for an epoch. Now, the input to this optimization problems are workload characteristics, pricing information, and network latencies. So within workload characteristics, the parameters are the availability requirements, the latency requirements, predicted arrival rate, read-write ratio on the key, size of the objects, and pricing is what we saw earlier, like pairwise network costs, VM cost for compute, and storage costs. The objective of the optimization is to minimize the expected cost over the next approach while maintaining the latencies, tail latencies. And the cost consists of sum of the compute cost, the storage cost, and the networking cost. And the output of the function is a cost optimal configuration. So it consists of which protocol to use, ABD or CAS, protocol parameters that would include how big is the quorum, how many replicas to use, or how big is the quorum, and which data centers to use for the quorum. And the constraints for optimization are latencies, consistency requirements, which are imposed via quorum sizes, and availability, which is fault tolerance. Another feature of the design is reconfiguration. So configuration for a key is reevaluated when the latency targets are violated or cost is suboptimal, which is detected for a sustained period of time. And it can happen due to maybe there's a data center failure or a change in client behavior. So we suddenly have new clients emerging in locations that were not sending traffic previously, or the ratio between read-write requests has changed. And reconfiguration happens when the new configuration is not the same as old configuration. So this paper proposes a reconfiguration algorithm that works with ABD and CAS. And the design goal is to minimize the impact on client performance during reconfiguration. Uh, it's done within 2 round trip time to controller for the ABD. And it enables quick transition to new configuration. So no waiting for ongoing operations to terminate. And the paper proves that the reconfiguration still preserves strong consistency. Now, some of the key results and insights from this. So for the experimental setup, the system was run over 9 data centers over GCP, and there were 500 workloads run with diverse features like arrival rate, read-write ratio, and latency. The baseline was replication only and with pricing and latency agnostic methods. So in the results, the author saw cost savings of between 5 and 60%, which is coming from significant savings in networking costs. Some of the insights from the paper were that the algorithms and parameters are not that straightforward to choose. So over here, on the x-axis, we have the traffic originating from mostly 1 or 2 locations. And on the y-axis, we have the latency targets. And the color coding is here. So red means the latency target cannot be satisfied if this data center contains the data and the client. Whereas when the traffic is write heavy, a high number of writes with very little gets, the algorithm prefers using ABD, which, if you remember, is replication. And then as the traffic shifts towards higher read and lower write, then the transition happens from replication to erasure coding. So the system prefers erasure coding as it thinks that the cost is optimized using erasure coding. And for some parameters, value of k is chosen as 1, which is the same as replication. However, due to structural differences in CAS and ABD protocols, the system comes to the conclusion that CAS replication is cheaper than ABD replication. And as the traffic shifts more towards read, it prefers erasure coding with K greater than 1. So some of the other insights were that the highest value of K is not optimal. So as the number of chunks in erasure coding increase, the network and storage cost decrease. However, the compute cost increase as the quorum size also increases. So the machine needs to handle more traffic, and as a result, the compute costs go up. The paper explores the model for finding an optimal K based on object sizes and arrival rate. And erasure coding does not always incur a latency penalty or a replication. So since ABD, it's a quorum-based approach, so the farthest data center determines the tail latency. But if multiple data centers are available which has similar internetwork latency and cost characteristics, then CAS, which is erasure coding, can offer same latency but with reduced costs. And here they discuss the reconfiguration aspect. So the traffic is coming from Tokyo, Sydney, Singapore, and Frankfurt. So at 200 milliseconds, there is a 4-fold increase in the traffic. So as a result, there is a reconfiguration that happens, and there is a slowdown observed due to reconfiguration. And at 400 milliseconds, a data center failure is simulated, which triggers a reconfiguration. And the reconfiguration completes within 1 second. However, there are clients which cache the reconfiguration, the configuration parameters, and they require at least a 1 round trip time to update their cache. So some of the slowdown is observed due to that. So I think that's pretty much what I had for. Thank you for dialing in. I'll stop sharing now.